Harmonics are electrical distortions that can cause problems in electrical systems. However, harmonics are generally less problematic in single-phase systems than in three-phase systems due to several reasons. One reason is the cancellation of harmonics. In a three-phase system, the harmonic currents generated by nonlinear loads in each phase can partially cancel each other. This is because the phase angles of the harmonic currents are shifted by 120 degrees in a three-phase system. However, in a single-phase system, there is no phase cancellation, and the harmonic currents add up directly. Another reason is the reduced amplitude of harmonics. The amplitude of harmonic currents is generally lower in single-phase systems than in three-phase systems. This is because the total harmonic current in a three-phase system is the vector sum of the harmonic currents in each phase. Since the harmonic currents in each phase are shifted by 120 degrees, the vector sum of these currents is typically smaller than the sum of the individual harmonic currents. Also, there is lower system impedance. Single-phase systems typically have lower impedance than three-phase systems. This lower impedance helps to reduce the magnitude of harmonic voltage distortions caused by harmonic currents. While harmonics can occur in both single-phase and three-phase systems, they are generally less problematic in single-phase systems due to the cancellation of harmonics, reduced amplitude of harmonics, and lower system impedance. Harmonics are unwanted currents or voltages that are integer multiples of the fundamental frequency of the electrical system. For example, if the fundamental frequency is 60 Hz, then the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. These harmonics are typically generated by nonlinear loads, which are devices that draw current in a non-sinusoidal manner. Examples of nonlinear loads include electronic devices such as computers, televisions, and fluorescent lighting, as well as industrial equipment like variable frequency drives and uninterruptible power supplies. Harmonics can cause a variety of problems in electrical systems. They can lead to increased heating in conductors and equipment, which can reduce their lifespan and increase the risk of failure. Harmonics can also cause voltage distortion, which can affect the performance of sensitive electronic equipment and lead to malfunctions. Furthermore, harmonics can interfere with communication systems and cause inaccurate readings in metering equipment. In three-phase systems, the harmonic currents generated by nonlinear loads in each phase can partially cancel each other out. This cancellation effect occurs because the phase angles of the harmonic currents are shifted by 120 degrees in a three-phase system. For example, if the third harmonic current in phase A is 10 amps at an angle of 0 degrees, the third harmonic current in phase B will be 10 amps at an angle of 120 degrees, and the third harmonic current in phase C will be 10 amps at an angle of 240 degrees. When these three currents are added together vectorially, the resulting current is significantly smaller than the sum of the individual currents. This cancellation effect is most pronounced for odd triplet harmonics, which are harmonics that are odd multiples of the third harmonic, such as the third, ninth, and 15th harmonics. These harmonics are particularly problematic because they can cause neutral currents to increase significantly in three-phase systems. In single-phase systems, there is no phase cancellation of harmonic currents. This is because there is only one phase, so all the harmonic currents add up directly. As a result, the harmonic currents in single-phase systems can be significantly higher than in three-phase systems. However, the overall impact of harmonics is often less severe in single-phase systems because the total amount of power being delivered is typically much smaller. The amplitude of harmonic currents is generally lower in single-phase systems than in three-phase systems. This is because the total harmonic current in a three-phase system is the vector sum of the harmonic currents in each phase. Since the harmonic currents in each phase are shifted by 120 degrees, the vector sum of these currents is typically smaller than the sum of the individual harmonic currents. In contrast, the harmonic currents in a single-phase system add up directly, so the total harmonic current can be higher. However, the overall impact of harmonics is often less severe in single-phase systems because the total amount of power being delivered is typically much smaller. Single-phase systems typically have lower impedance than three-phase systems. Impedance is the opposition to the flow of alternating current, and it is determined by the resistance and reactance of the circuit. Lower impedance helps to reduce the magnitude of harmonic voltage distortions caused by harmonic currents. This is because the voltage distortion is equal to the product of the harmonic current and the impedance of the circuit. Therefore, if the impedance is lower, the voltage distortion will also be lower. In summary, harmonics are generally less problematic in single-phase systems than in three-phase systems due to the cancellation of harmonics, reduced amplitude of harmonics, and lower system impedance. However, it is important to note that harmonics can still cause problems in single-phase systems, especially if there are a large number of nonlinear loads. Therefore, it is always a good idea to assess the harmonic levels in any electrical system and take steps to mitigate them if necessary. Mitigation techniques for harmonics include the use of harmonic filters, which are devices that block or reduce the flow of harmonic currents. Harmonic filters can be installed at the source of the harmonic currents, such as at the output of a variable frequency drive, or they can be installed at the point of common coupling, which is the point where the electrical system is connected to the utility grid. Another mitigation technique is the use of harmonic reducing transformers, which are transformers that are designed to reduce the amount of harmonics that are generated by nonlinear loads. Harmonic reducing transformers can be more expensive than standard transformers, but they can provide significant benefits in terms of reduced harmonic levels and improved power quality. Furthermore, proper grounding and wiring practices can help to reduce the impact of harmonics on electrical systems. This includes ensuring that all equipment is properly grounded and that the wiring is sized appropriately for the expected harmonic currents. In addition to these mitigation techniques, it is also important to implement regular monitoring of harmonic levels in electrical systems. This can be done using harmonic analyzers, which are devices that measure the amplitude and frequency of harmonic currents and voltages. By monitoring harmonic levels, it is possible to identify potential problems early on and take corrective action before they cause significant damage or disruption. In conclusion, harmonics are a potential problem in both single-phase and three-phase systems, but they are generally less problematic in single-phase systems due to the cancellation of harmonics, reduced amplitude of harmonics, and lower system impedance. However, it is important to take steps to mitigate harmonics in any electrical system, especially if there are a large number of nonlinear loads. By implementing proper mitigation techniques and monitoring harmonic levels, it is possible to ensure the reliable and efficient operation of electrical systems. To understand the difference between single-phase and three-phase systems regarding harmonics, it's essential to delve into the specifics of each system and how harmonics behave within them. Single-phase systems, commonly found in residential and small commercial applications, typically supply power through two wires, a phase wire and a neutral wire. The voltage oscillates in a sinusoidal waveform at a specific frequency, usually 60 Hz in North America. Nonlinear loads, such as electronic devices, computers, and LED lighting, draw current in a non-sinusoidal manner, creating harmonics. These harmonics are integer multiples of the fundamental frequency. For instance, the third harmonic of a 60 Hz system is 180 Hz, the fifth is 300 Hz, and so on. In a single-phase system, these harmonic currents flow directly through the phase and neutral wires. Since there is no other phase to counteract or cancel these harmonics, they add up directly. This can lead to increased current in the neutral conductor, overheating of transformers, and voltage distortion at the point of connection. However, because single-phase systems generally handle lower power levels compared to three-phase systems, the overall impact of harmonics might be less severe. Three-phase systems, widely used in industrial and large commercial applications, utilize three separate phase conductors, each carrying an alternating current that is 120 electrical degrees out of phase with the others. This configuration offers several advantages, including more efficient power delivery and the ability to supply high power loads. Harmonics in three-phase systems behave differently due to the phase relationships between the three phases. Specifically, triplet harmonics, which are odd multiples of the third harmonic, such as the third, ninth, 15th, and so on, have a unique characteristic. These harmonics are in phase with each other in all three phases. As a result, they do not cancel out in the phase conductors. Instead, they add up in the neutral conductor, potentially causing a significant increase in neutral current. This is a major concern in three-phase systems because an overloaded neutral conductor can lead to overheating, insulation damage, and even fire hazards. Non-tripling harmonics, such as the 5th, 7th, 11th, and 13th, do not add up directly in the neutral conductor. Instead, they tend to circulate within the three phases, creating circulating currents that can cause additional losses and voltage distortion. One of the key reasons why harmonics are often considered less problematic in single-phase systems compared to three-phase systems is the potential for cancellation in three-phase systems. While tripling harmonics do not cancel and can cause neutral current issues, other harmonics can partially cancel each other out due to the 120-degree phase shift between the phases. This cancellation effect reduces the overall harmonic distortion in the system. Another factor is the lower system impedance typically found in single-phase systems. Impedance is the opposition to the flow of alternating current and includes both resistance and reactance. A lower impedance helps to reduce the magnitude of harmonic voltage distortions. Since voltage distortion is the product of harmonic current and impedance, a lower impedance results in lower voltage distortion for the same level of harmonic current. Despite these advantages, harmonics can still pose problems in single-phase systems, especially with the increasing use of nonlinear loads. Therefore, it is crucial to implement appropriate mitigation techniques to minimize the adverse effects of harmonics. Some common mitigation techniques include, firstly, harmonic filters. These filters are designed to block or reduce the flow of specific harmonic frequencies. They can be installed at the source of the harmonic generation or at the point of common coupling where the system connects to the utility grid. Secondly, harmonic reducing transformers. These transformers are specifically designed to minimize the generation and propagation of harmonics. They employ various techniques, such as special core designs and winding configurations, to reduce harmonic distortion. Thirdly, proper grounding and wiring practices. Proper grounding and wiring techniques can help to minimize the impact of harmonics on the system. This includes ensuring that all equipment is properly grounded, using appropriately sized conductors, and minimizing the length of conductors. Fourthly, power factor correction. Improving the power factor of the system can also help to reduce harmonic distortion. Power factor correction capacitors can reduce the amount of reactive power flowing in the system, which can, in turn, reduce harmonic currents. Fifthly, active harmonic filters. These filters use electronic components to actively inject current waveforms that are equal in magnitude but opposite in phase to the harmonic currents. This effectively cancels out the harmonics and reduces distortion. Sixthly, line reactors and DC chokes. These devices can be installed in series with nonlinear loads to reduce the magnitude of harmonic currents. Line reactors are typically used on the AC side, while DC chokes are used on the DC side of equipment like variable frequency drives. To effectively manage harmonics, it is essential to conduct a thorough harmonic analysis of the electrical system. This analysis involves measuring the harmonic currents and voltages at various points in the system to identify the sources of harmonics and assess the level of distortion. Based on the results of the harmonic analysis, appropriate mitigation techniques can be selected and implemented. Regular monitoring of harmonic levels is also crucial to ensure that the mitigation techniques are effective and to detect any changes in harmonic distortion over time. This can be achieved using harmonic analyzers, which are specialized instruments designed to measure harmonic currents and voltages. In conclusion, while harmonics are generally considered less problematic in single-phase systems compared to three-phase systems due to factors such as potential cancellation and lower system impedance, they can still pose challenges, especially with the proliferation of nonlinear loads. Implementing appropriate mitigation techniques and conducting regular harmonic analysis are essential for maintaining power quality and ensuring the reliable operation of electrical systems. It's also crucial to stay informed about the latest standards and best practices related to harmonic mitigation, as technology and understanding of harmonics continue to evolve. Consider, for example, the implications of harmonic currents in specific types of equipment and applications. In variable frequency drives or volts, for instance, the rapid switching of power semiconductors generates significant harmonic currents. These harmonics can propagate back into the power system, causing voltage distortion and potentially affecting other equipment connected to the same grid. In data centers, the high density of electronic equipment, such as servers and network devices, creates a significant harmonic load. The resulting harmonic currents can lead to increased energy consumption, overheating of equipment, and reduced system reliability. In hospitals, sensitive medical equipment is particularly susceptible to voltage distortion caused by harmonics. This can lead to inaccurate readings, equipment malfunctions, and potential risks to patient safety. In industrial facilities, large motors, welders, and other heavy equipment can generate substantial harmonic currents. These harmonics can interfere with communication systems, cause premature failure of equipment, and increase energy costs. Understanding the specific challenges and mitigation strategies for harmonics in these diverse applications is essential for electrical engineers and technicians. It also highlights the importance of collaboration between different disciplines such as power systems, electronics, and communications to effectively address harmonic-related issues. It is also very important to consider the economic impact of harmonics. Increased energy consumption, equipment failures, and downtime can lead to significant financial losses for businesses and industries. Investing in harmonic mitigation techniques can not only improve power quality and system reliability, but also provide a significant return on investment through reduced energy costs, extended equipment lifespan, and minimized downtime. Finally, it's essential to consider the environmental impact of harmonics. Increased energy consumption due to harmonics contributes to greenhouse gas emissions and other environmental problems. By mitigating harmonics, we can reduce energy consumption and improve the overall sustainability of electrical systems. Therefore, addressing harmonics is not only a technical and economic imperative but also an environmental responsibility. So to reiterate, harmonic currents are less of a problem in single-phase circuits than in three-phase circuits. Single-phase circuits have no phase shift of current to allow the current to cancel out. In general, single-phase circuits also have a lower impedance and reduce the magnitude of harmonic voltage distortions caused by harmonic currents.